In the previous section, we learned about bases. Now remember, a basis of a vector space is a set of vectors that span that vector space and that are linearly independent, right? So in this section, we're going to explore bases a little bit. So let's just think about this geometrically for a moment. Say I have two vectors. This vector here and maybe this vector here. Okay? Now, these two vectors, if we put them together, what space does it span? Well, it would span a line, right? Together, if you take any linear combination of those vectors, you could get any vector along that line. But notice, are both vectors really necessary for this? Well, no. If I take one out, it would still span the line, right? So this isn't a basis. In other words, these two vectors are not a basis for this line, right? This vector space. If I take just one of the vectors, then any linear combination of this, which means any scalar multiple of this, lies along this line also, right? So for a line, this particular basis can be represented with only one vector. Okay? And if you think about it, whenever you have one vector, if you take the span of just one vector, you're going to get a line, right? Because you could stretch that vector in as long as you want or flip it around by just taking a scalar multiple of it. But what if the vectors aren't on the same line? What if I have a vector here and another vector maybe here? Okay, well, in this case, if I take the vectors together, because they're not pointing in the same direction, they span a plane. So any point in the plane is going to be spanned by these two vectors. Now the question is, do these two vectors form a basis for this plane? Okay, so imagine adding another vector. If we were to add another vector, would that vector really be contributing anything? Well, no, it's still in the plane, right? So any linear combination of the three vectors would be the same as the linear combination of these two vectors. So these three vectors must not be linearly independent. There's a redundant vector there. There's an extra vector. That new vector isn't adding any new information. But similarly, if I were to take one of these vectors away, then I wouldn't be spanning the whole plane anymore. I'd only be spanning a line, right? So what we're noticing is that it seems like one vector, that the span of one vector is a plane, or I'm sorry, not a plane. The span of one vector is a line. That if we take a line through the origin, a basis for that subspace is just one vector. Similarly, if we take the entire plane in R2, a basis for that plane is two vectors that aren't pointing the same direction. Okay? It turns out this is a general rule, that if you have a basis for a vector space, if you have two different bases, they have to have the same number of vectors in those bases.